Hello students, welcome to class 11 physics. In this video we are going to solve some of the numerical of textual illustration of chapter number 5 laws of motion. 5.6 See figure A mass of 6 kg is suspended by rope of length 2 meter from the ceiling. A force of 50 Newton in the horizontal direction is applied at the midpoint P of the rope as shown. What is the angle the rope makes with the vertical in equilibrium? Take G equals to 10 meter per second square and neglect the mass of the rope. So here as you can see that the rope is tied to the rigid support and to the other end a mass is suspended and its weight is given, that is 6 kg, and the length of the rope is 2 meter, and exactly at the midpoint of the length, that is at 1 meter, force is applied to the rope in the horizontal direction and the force is 50 Newton. So here we need to find the angle that is made by the rope in the vertical direction, because it moves like this, it makes the angle theta in the with the vertical axis. So that theta we need to find over here. So first of all let us see the free body diagram. First of all, free body diagram of the weight. Just we are seeing the free body diagram of the weight. So on the weight, that is on the object, two types of forces will be acting. One is the weight of that which is in downward direction, and the tension that is in the upward direction, tension prevailing in the rope that is towards the fixed end. So it is in the upward direction. Now let us see the free body diagram of P. Free body diagram at point P. So here at point P, forces that is acting. First of all, the tension 2 that is prevailing in the rope towards the edge, that is towards the block. Another tension prevailing towards the fixed end, that is in this direction. Now because it is neither in horizontal nor in the vertical axis, we need to take the component, and here we know that this tension T1, it makes the vertical axis with vertical axis angle theta. So when you take the projection of T1 on this axis, that will give you the horizontal component, that is T1 cos theta, and when you take projection of the vector on the other axis, that will give you the vertical component, that is T1 sin theta, as well as the force is applied on this P in this direction, which is 50 Newton. So we are having 50 Newton and T1 sin theta in the horizontal direction, T2 and T1 cos theta in the vertical direction. So taking the equilibrium condition, for equilibrium of W, we get T2 equals to mg, because T2 is in upward direction, mg that is in downward direction. So we can write T2 equals to mg. So 6 into 10, that is 60 Newton. So tension T2, that is 60 Newton. Now at point P, there are two components of T1, vertical component T1 cos theta and balances T2, and horizontal component T1 sin theta, which balances 50 Newton. So for equilibrium of P, we can see in the vertical direction, T2 is in downward direction, T1 cos theta is in upward direction. So from this we can write T1 cos theta equals to T2. So T1 cos theta is equals to T2, we got value as 60, so putting that, so T1 cos theta equals to 60. Now from the figure we can see that in horizontal direction T1 sin theta is in this direction, 50 Newton in the other direction. So we can write T1 sin theta equals to 50 Newton. So here T1 sin theta equals to 50. And also using this equation, T1 cos theta equals to 60 and T1 sin theta equals to 50. So T1 taking the division, taking the ratios, T1 sin theta equals to 50 by T1 cos theta equals to 60. So that will be T1 sin theta upon T2 cos theta equals to 5 by 6. That is, this becomes tan theta. So T1 upon T2, that is tan theta equals to this 5 by 6, that will be equal to 0.8333. Here the tension will be same, so cancelling it out we get tan theta equals to 0.8333. So theta will be 39 degree 48 minute. Or when you approximate it, when you round off that, we can also write it as 40 degree. Here we see that result do not depend on the length of the rope or position of the horizontal force. So students, you may copy down this numerical. Now numerical number 5.7. Determine the maximum acceleration of the train in which a box lying on its floor will remain stationary. Given that the coefficient of static friction between the box and the train's floor is 0.15. So here we need to find the maximum acceleration of the train such that even if the train is moving in one direction, the box lying inside the train compartment on the floor, it should not move. So friction is provided by the floor of the train such that this box will not move. So what will be the maximum acceleration with which it can move such that the box should not move? It should be stationary. So due to the static friction, block will get acceleration. So equation is static friction, that is Fs equals to F, and here F equals to ma and Fs equals to mu s n, where n is nothing but that is mg. Why n is equals to mg? Here the static friction provided by the external force Fs is equals to F, F is equals to ma, and here static friction is equals to mu s n. Now we know that the object is not moving, so two forces acting on that is W, that is weight in the downward direction, and n in the upward direction, that is the normal force. So here by the equilibrium condition we can write n equals to W, that is W is equals to mg. So we can write n equals to mg. So Fs equals to F, that is mu s, n equals to ma, so mu s mg equals to ma. M gets cancelled, we are having mu s g equals to a, that is the maximum acceleration, as you can see over here. A max is equals to mu s g. Mu s, that is the coefficient of static friction, which is equals to 0.15. Into gravitational acceleration we need to take it as 10, as the hint is given over here. So value is 1.5 meter per second square. So this is the maximum acceleration of the train in which the box lying will be stationary, will remain stationary. So students, you may note down this numerical.